Getting to Mars is already an enormous challenge, but returning from Mars is an entirely different problem. You have to escape Mars's gravity, launch from a planet with almost no infrastructure, carry enough fuel for the journey home, and survive a trip of tens of millions of kilometers back to Earth. Every kilogram of fuel you need to return must somehow already be waiting for you on Mars, or you must carry it with you from the beginning. This kind of problem, where a simple idea becomes unbelievably complicated when you examine the physics, was exactly the kind of thing that fascinated Richard Feynman. He loved pointing out that nature doesn't care about our dreams or ambitions. It follows strict physical laws. And when those laws involve gravity, fuel, and energy, the universe can make even the boldest plans surprisingly difficult. To understand why returning from Mars is such a difficult challenge, we first have to think about gravity and energy. Every planet has gravity, and gravity acts like a kind of invisible well. The deeper you are inside that well, the harder it is to climb out. Rockets do not simply fly upward like airplanes. They must generate enough energy to escape the gravitational pull of the planet they are on. Mars has weaker gravity than Earth, but it still has a significant gravitational pull. The escape velocity of Mars is about 5 kilometers per second. That means any spacecraft leaving Mars must reach at least that speed to break free from the planet's gravity and continue traveling into space. Reaching that speed requires an enormous amount of energy, and in rocketry that energy comes from fuel. This is where the problem begins to grow. To send a rocket from Mars back toward Earth, the spacecraft must carry fuel to power the engines that accelerate it to escape velocity. But fuel itself has mass, and that mass makes the rocket heavier. A heavier rocket requires even more fuel to accelerate it. As the rocket becomes heavier, the amount of fuel needed continues to increase. This is a classic challenge in rocket physics. When engineers design a mission to Mars, they must carefully calculate how much fuel is needed for each phase of the journey. A spacecraft traveling from Earth to Mars must first escape Earth's gravity, then adjust its trajectory through space, and finally slow down enough to land safely on Mars. But if astronauts want to return, an entirely new rocket launch must take place from the Martian surface. Launching from Mars is not like launching from Earth, where there are launch pads, fueling systems, factories, and thousands of engineers. Mars has none of these things. Everything needed for the return trip must either be transported there ahead of time or somehow produced on the Martian surface. Imagine landing on Mars with a spacecraft that must later take off again. The engines must still function perfectly. After months on a cold, dusty planet, the fuel must remain stable and usable. The rocket structure must survive the harsh Martian environment, including temperature extremes and fine dust that can interfere with mechanical systems. Even the act of launching is complicated. A returning spacecraft must ignite its engines on the surface, accelerate upward through the thin Martian atmosphere, and reach the necessary speed to escape Mars's gravitational pull. During this climb, the rocket must remain stable, maintain the correct direction, and conserve enough fuel to complete the journey. Once the spacecraft escapes Mars, the journey is not finished. The rocket must also set itself on a trajectory that will intersect with Earth's orbit at the correct time. Space travel is not like driving directly from one city to another. Planets are constantly moving along the orbits around the Sun, so the spacecraft must follow a carefully calculated path that allows it to meet Earth months later. All of these challenges make the return trip far more complicated than it might appear at first glance. It is not simply a matter of flying back the way you came. The laws of physics, especially those involving gravity and energy, create strict requirements that every spacecraft must obey. Physicists such as Richard Feynman often emphasized that nature operates according to precise rules. Rockets cannot negotiate with gravity or ignore the energy required to escape a planet. Every kilogram of mass must be lifted out of the gravitational well, and every increase in weight demands additional fuel and power idea. These physical realities turn the dream of returning from another planet into a complex engineering challenge that requires careful planning, enormous resources, and the deep understanding of how motion and energy work in space. One of the most important ideas in space travel is something known as the rocket equation. This principle describes how rockets gain speed by throwing mass, usually in the form of burning fuel, out of their engines at very high velocity. The basic idea sounds simple. Fuel burns, hot gases rush out the back of the rocket, and the rocket is pushed forward. But the mathematics behind this process reveals a surprising and challenging reality. The rocket equation shows that the amount of fuel required to reach a certain speed increases extremely quickly as the desired speed grows. This means that to travel faster, a rocket must carry much more fuel. But carrying more fuel makes the rocket heavier, and the heavier rocket requires even more fuel to accelerate. The relationship becomes a kind of chain reaction where weight and fuel demands increase together. This principle becomes especially important when planning missions between planets. A spacecraft traveling from Earth to Mars must accelerate enough to escape Earth's gravity and move on to a trajectory around the Sun that eventually intersects with Mars. That journey already requires a large amount of fuel. But if astronauts want to return from Mars, the spacecraft must also carry or obtain enough fuel to launch again and repeat a similar process in reverse. Here is where the difficulty grows dramatically. The rocket that leaves Mars must carry fuel not only for the initial launch from the Martian surface, but also for adjusting its course during long trip back toward Earth. Engineers must calculate how much speed the spacecraft needs, how long the journey will take, and how the positions of Earth and Mars will change during that time. According to the rocket equation, even a modest increase in required speed demands a significant increase in fuel mass. Because of this, spacecraft are usually designed with multiple stages. As each stage finishes burning its fuel, it is discarded, making the remaining rocket lighter and easier to accelerate. This method helps reduce the total fuel required, but it also adds complexity to the mission. Now imagine trying to apply the system on Mars. If astronauts plan to return to Earth, they must either bring a fully fueled return rocket with them, or find a way to produce the fuel on the Martian surface. Bringing all the fuel from Earth would make the spacecraft extremely heavy during the outbound journey. Producing fuel on Mars would require advanced equipment capable of extracting resources from the planet's environment and converting them into rocket propellant. Even if such systems work perfectly, the rocket equation still imposes strict limits. Engineers must carefully balance the weight of the astronauts, life support systems, scientific equipment, fuel tanks, engines, and structural components. Every kilogram added to the SEP. As craft increases the amount of fuel needed for the return trip, this challenge illustrates why space missions are designed with such precision. Engineers must calculate regas fuel requirements and launch windows years in advance. The timing must be exact because Earth and Mars are constantly moving in their orbits around the Sun. If a spacecraft misses the correct alignment, the amount of fuel required to correct the course could become impractically large. The rocket equation does not care about human ambitions or dreams of exploration. It simply describes how momentum and mass behave according to the laws of physics. Rockets must obey these rules no matter how advanced the technology becomes. Physicists like Richard Feynman often enjoyed pointing out that nature sets firm boundaries through its laws. Understanding those laws does not make exploration impossible, but it reveals why such missions are incredibly challenging. The rocket equation shows that returning from another planet is not just a matter of building a powerful engine. It is a delicate balance between speed, mass, and fuel, where even small changes can dramatically alter what is possible in space travel. When thinking about the challenges of traveling between planets, one idea that physicists often emphasize is that nature sets strict rules for how motion and energy work. Human imagination can design bold missions and ambitious journeys, but those plans must ultimately follow the laws of physics. This perspective was very common in the thinking of Richard Feynman, who frequently reminded people that the universe does not adjust its laws to make our plans easier. Interplanetary travel is not simply a matter of building a powerful rocket and pointing it toward another planet. Every movement through space requires careful planning and enormous energy. The distances involved are vast, and the gravitational forces of planets and the sun shape the path spacecraft must follow. One of the key difficulties in returning from Mars lies in the idea of energy balance. A spacecraft traveling from Earth to Mars must first climb out of Earth's deep gravitational well. That step alone requires tremendous energy and a powerful launch system. After escaping Earth, the spacecraft must enter an orbit around the Sun that intersects with Mars's orbit at the correct time. But when the astronauts arrive on Mars, the journey is only half finished. If they want to return home, they must repeat many of those steps again, but this time starting from the surface of another planet with far fewer resources. The spacecraft must launch from Mars, escape the planet's gravity, and then adjust its trajectory to intersect with Earth's orbit months later. The challenge is not only the fuel required, but also the reliability of every system involved. A mission to Mars would take many months just to reach the planet. Astronauts might remain there for a long period while waiting for the correct alignment of the planets that allows a return trip with reasonable fuel use. During that time, the spacecraft intended for the return journey must remain functional in an environment that is extremely hostile to machinery. Mars is cold, dusty, and exposed to radiation. Fine dust particles can cover equipment and interfere with mechanical systems. Temperatures can drop far below what many materials normally experience on Earth. Over a long period, these conditions could affect engines, fuel systems, electronics, and structural components. When the time comes to return, the astronauts would depend completely on the success of that launch from Mars. Unlike missions launched from Earth, there would be no immediate rescue options. If something went wrong with the engines, the fuel supply, or the launch process itself, the crew would be stranded millions of kilometers away from home. This reality highlights a deeper lesson about exploration. Space travel demands extraordinary precision because the margin for error is extremely small. Every stage of the mission must function exactly as planned. A small miscalculation in fuel timing or trajectory could mean the difference between a successful return and being unable to leave the planet. Feynman often appreciated examples where simple physical principles lead to enormous practical consequences. The laws governing gravity, motion, and energy are straightforward when written in equations, but applying them to real missions reveals just how demanding those laws can be. Rockets must carry fuel, engines must work reliably, and trajectories must be calculated with incredible accuracy. The dream of traveling to Mars is one of humanity's most exciting ambitions, but the physics behind that dream reminds us that the universe operates according to strict rules. Any mission attempting to leave another planet and return safely to Earth must overcome challenges created by gravity, distance, fuel limitations, and the unforgiving conditions of space. So when we imagine humans standing on the surface of Mars, it's easy to focus on the excitement of the journey there. But the real challenge often lies in the journey back. Escaping a planet carrying enough fuel, surviving harsh conditions, and navigating millions of kilometers through space are problems that must all be solved perfectly. The laws of physics set strict limits, and every successful mission must work within those limits. This is why space exploration demands careful planning, powerful technology, and a deep understanding of how nature actually works. It's the kind of reality that fascinated Richard Feynman. The idea that behind every ambitious dream there are fundamental rules that they cannot be ignored, yet those same rules also guide us to our solutions if we study them closely enough.